Here in lecture B, we're going to go back to motion, but we're not doing parametric curves today. I'm saving that for Wednesday and Friday. The motions we're going to consider here, therefore, are simpler. Today's simpler to try to get across the same main big points that I was making with parametric curves. Especially that the integral of the speed is the distance traveled. But we're going to generalize that, actually, to situations where you might have back and forth motion. Linear motion in one dimension, sometimes positive if you're moving to the right, say, and sometimes negative if you're moving to the left. Or if you're going up and down, say the upward direction is positive velocity and the downward direction would be negative velocity. So again, we're going to just consider one-dimensional back and forth motion today, though initially it'll just be one direction. All right, let's get this down here. This is really key. Suppose y equals f of t is the position in meters of an object along the y-axis as a function of time. So I am going to be imagining vertical motion here. And on Wednesday, that'll be, I'm going to show you some mathematical things that'll illustrate this in nice ways. So there's like a y-axis, and you've got motion of some object along the y-axis. If it's moving upward, that's a positive velocity. When it moves upward. When it moves downward, it would be a negative velocity. And if it's not moving, that would be a zero velocity. Though, as we've seen before, zero velocities can sometimes occur just for one instant of time, like when you throw something up in the air and let it come back down. But the instant when it reaches its peak, a high point, at that instant the velocity is zero. We already know the velocity is the derivative of this, right? That's something we know before. Leibniz notation for the derivative would be dy dt. That's f prime of t. That's the derivative of this function. That's the position. We could also call this v for velocity. And I'm putting something extra in here. I'm putting a v of t in here as another way to emphasize the velocity as a function of time. Now, I didn't have to do that. And in fact, in some ways, it's not good to do that, because the letter v is representing two things here. It's representing both a dependent variable, a number, and a function name. So this is called an abuse of notation. Not abusive notation, but an abuse of notation. The same letter is representing two slightly different things, but scientists do it all the time. And the main thing is just not to let it bother you. V represents both the dependent variable and the function name whenever I want to. Okay? Just don't let it bother you. When I was in your shoes, it bothered me. Don't let it bother you. That's the main lesson. Okay? It's not a big deal. It is sloppy, but people do it. Since the indefinite integral, or since indefinite integration is the reverse process of differentiation, we can also undo this by integrating. We can write this equation. The original function is the indefinite integral of the velocity. The velocity is also the derivative of the original function. Again, indefinite integrals are called indefinite because they're not definite functions. They're families of functions, plus c, where the c can be anything. However, to get the particular position function, you'd have to choose an appropriate c, not any c. It would have to be one particular one. I'm just not saying what it is. It would depend on the situation. We're going to look at examples. What's new now, though, is we're also saying something else. We're also saying, at least in the case when the velocity is positive, that the distance traveled is the area under the velocity graph. And we write, assuming we start at y equals 0 when t is a, we write it as a definite integral. And you can describe it in words as the definite integral of the velocity over the interval from a to t. I'm implicitly assuming t is bigger than a. Though it actually can apply to situations even when t is less than a. A most typically is 0. but it doesn't have to. Usually you start at time 0, but you don't have to actually. It's the area under the graph. The definite integral of this velocity is the area under the graph of the velocity. If I graph the velocity as a function of time, and say some arbitrary wiggly graph like this, which would represent speeding up and slowing down and speeding up and slowing down, all in one direction because it's always positive. I'm going to abuse notation again and use the same letter t to represent both an axis and a particular number. This area under the graph, that area equals the original position function at that value of t. But this t can change, so this is really a function of t. This area can change as you move this value of t back and forth. The fundamental theorem of calculus is really getting at the connection between the indefinite integral, antiderivatives, and area on the graphs. This again is the notation. And again, the u is just a dummy variable. I can use anything here. Good choices for the variable would be anything but a or t or d or b. Use a common letter to use. The variable for this is the upper limit of the integral. What you want to imagine is I can slide this t back and forth and change the area. That's what you want to imagine. Telling you exactly what you want to imagine. So you need to work on it. You need to think about it. And we'll think about it with some examples here. Again, this is the essence of the fundamental theorem of calculus, FTC. In what's actually its harder version, so to speak, that chapter 6 section, 6.4, I had you do a few problems about it. They call that section the second fundamental theorem of calculus, and they label the theorem as the construction theorem for antiderivatives. But it really is the fundamental theorem of calculus. There are kind of two forms of it. I'm actually introducing you to the one that people typically think of as hard. The definite integral symbol represents the area under the function. And then putting the t up there as a variable means this is a function of t, that it's going to be an antiderivative of the original function. If I differentiate this, I get the original function. I can write this equation too. I get that. If I differentiate the distance traveled, I get the velocity, or speed if it's motion in one direction. Let's look at some examples, and we'll build up in more complexity. Constant velocity example. Let's say the velocity is always 3. And I'm purposely not starting at t is 0. I'm starting at a different value of t. T is 1. On purpose, just to do something different. Again, not that you have to. When you're trying to use the stuff in real life, typically you start t at 0. But in theory, you can start t at any moment in time. I'm choosing to start it at t equals 1. Let's assume we do start at position 0 though. So if we're talking about up-down motion, along a vertical y-axis, y equals 0 could be the ground. That would be the most natural thing to do. And if the position becomes negative, it did so because maybe you have a hole in the ground, right? You dug a well. Then the position could become negative. Be careful here. I'm not talking about gravity at all. Okay, so I'm not thinking about the force of gravity here. I'm only thinking about the motion itself, which could go up and down indefinitely. Maybe you're thinking about a bug that just decides to fly up and down all the time. Okay. So I'm not saying anything about gravity here. Now what can you say? like I said in the last slide, the integral, the definite integral of the derivative, which is the velocity, over the integral from 1 to t, that's going to be the area under the rectangle that's shown below right here. And that will be the position. The area will be the position. Or if you want to think of it as distance traveled, because it is always in one direction, velocity is always positive. It's a positive constant. In fact, this is motion in the positive direction at a constant speed. This is really nothing more than distance equals rate times time. Remember back from lecture 1? A lot of calculus is just generalizing that equation, distance equals rate times time. The rate is the height of the rectangle. Velocity, 3 meters per second, say. The base is the amount of time elapsed. Not equal to t in this case, though, because we're starting at time 1. This number right here at about 3.8 or so is t, but that's not the amount of time elapsed, because I started time at 1. The amount of time elapsed would be t minus 1. And what is the area of that rectangle? Base times height. The base is, again, not t. It's t minus 1. The height is 3. This is rate times time, except switched around. That's the rate, there's the time. And that simplifies to 3t minus 3. Notice that indeed is an antiderivative of the velocity. Integrate 3. You're going to get 3t plus c. Find the indefinite integral of 3. You get 3t plus c. The c in this case happens to be negative 3. Right there. Why? So that y equals 0 when t is 1. Y equals 0 when t is 1. When you plug in t is 1 there, you get 0. That's why. So it's not all the antiderivatives. I don't want a plus c there. I want a particular c. Right? In this case, minus 3. But this is a function whose derivative is always 3. If y were something other than 0 when t is 1, then this would be something other than minus 3. Like if y were 5 when t equals 1, what would the function be? The f of t would be 3t, here's probably the quickest way to figure it out, 3t minus 1 in parentheses plus 5. That's a function that equals 5 when t is 1. If you expand it out, it's 3t plus 2. That's a function that equals 5 when t is 1. So if you have a different initial condition, you get a different answer. Next example. Now we're doing a constant acceleration instead of a constant velocity. These are really important examples. You really, really, really want to make sure you understand this. Okay? So listen carefully. Suppose the velocity, v of t, which we can call f prime of t, is 2t plus 5. Once again, I'm not starting at t equals 0. I'm starting at t equals 3 this time. Just because. I'm just picking random numbers. Because I want to illustrate that you can think of it that way. Once again, let's assume y is 0 at the starting value of time. In this case, t equals 3. Once again, the definite integral is an area. In this case, it's an area under a trapezoid, or under the line, the region itself, you want to find the area of, is a trapezoid. Shaped like this. You can find the area of a trapezoid in two ways. You can break it into a rectangle and a triangle. Watch my finger here. There's a rectangle. And here's a triangle, a right triangle in fact. Find the area of the rectangle and triangle and add them up. A shortcut is you can take the base times the average of the two heights. Here's what that turns out to give you. Make sure you think carefully about each one of these steps here. Now, definite integral, which is the area that's shaded, must therefore be base times this is the average of the heights. Height 1 is this height. It doesn't depend on t. It's just this function when t is 3. Plug in t equals 3 into that function, you get 2 times 3 plus 5 is 6 plus 5 is 11, just like you see. That's 11. The other height is the function at this arbitrary value of t. Plug in that into the function, you get 2t plus 5. This line has a height of 2t plus 5. Because I'm not saying what t is. In my imagination, I want to imagine that I can change this. That's the second height. Here's the base. That distance right there. T minus 3, this is 3. This distance is t minus 3. Do some algebra to simplify this. 2t divided by 2 is just a t. 11 plus 5 is 16 divided by 2 is 8. Now expand that out. FOIL. T times t is t squared. Outside times outside is 8t. Inside times inside is negative 3t. Combine those, you get positive 5t. And then last times last is negative 3 times positive 8 is negative 24. That's a formula for the area as a function of t. Remember, I can change where this t is. I can move this back and forth. I can put it in Mathematica and manipulate it, and if we have time, I'll do that. I did in class today. Notice, hey, take the derivative of this. What do you get? 2t plus 5 minus 0. 2t plus 5. It is working. This is an antiderivative of the velocity. And it equals 0 when t is 3. Just like I wanted. Plug in 3 right there, you get 0. Times 11 is 0. Plug in t equals 3 right here, you get 9 plus 15 is 24, minus 24 is 0. And I can graph this function as well. I didn't take the time to do that. Maybe I should have. If you graph this function, this position function, the whole graph is a parabola with intercepts at 3 and negative 8, opening upward about like this. But we don't care about the whole graph. We only care about the part over here, when t goes from 3 to 6. Something like this. That's the part we care about. It is a curve, it's not straight, because it's part of a parabola. That's the position function, when t is between 3 and 6. And it does start at y equals 0 when t is 3. Next example is a non-constant acceleration. So again, so far we've done constant velocity, positive velocity. I'm walking to the right at a constant speed. Positive velocity because it's in the positive direction. The second example was a constant acceleration. The speed is not constant, you're speeding up, but the rate of change of the velocity is constant. Now it's non-constant acceleration. I made the velocity equal 3t squared. Now I am starting time at 0 because that's going to keep things simpler. Once again, let's assume y is 0 when t is at its starting value, which in this case is also 0. Once again, the definite integral is the area under a graph. In this case, the graph is a parabola. This is not the same as the graph that I drew on the board. The one that I drew on the board was from the other example on the previous slide. This is a new example. That was a position. This is a velocity. The graph is not straight. It's a quadratic. The acceleration is not constant. The derivative of the velocities, not constant. So the linear function would be 6t. But the principle still holds. The position is this area. And again, in your imagination, you want to imagine you can move this t back and forth, and maybe just in one direction, making the area change. If you move it to the right, the area is going to increase. The distance traveled is going to increase. And you're accumulating areas at a faster and faster rate over here when the graph is higher. The position function is actually going to be a cubic. It's going to be t cubed. And that does go through the origin. I'm saying it's t cubed. I'm not saying y in this case, though. I'm saying the position function is t cubed, which is an antiderivative of the velocity. Integrate 3t squared, you'll get t cubed plus c. C is going to be 0 because I want the graph of this function to go through the origin. This is a function whose derivative is the velocity, 3t squared. But I can't use formulas for areas of rectangles or trapezoids to find that area and say it equals t cubed. You're just trusting me. In fact, this is what got Newton and Leibniz really going, is realizing that you could find this area by doing an antiderivative of 3t squared and get t cubed. That's not obvious. Far from obvious that it should be t cubed, other than just using the knowledge that you know it's got to be an antiderivative. Okay. This even works when the velocity is sometimes or always negative, with a catch. It works with a catch. It doesn't work exactly in the same way, but in a similar way. This slide doesn't have any graphs. It's just general statements that we are going to apply in another slide that has graphs. If the velocity, v of t is f prime of t, is sometimes or even always negative in value, then this all still works with appropriate adjustments. The indefinite integral with an appropriate choice of c is still a position. Though I am emphasizing the word position now above distance. Because if the velocity is negative sometimes, I really after my change in position, not my distance traveled. So if you go back and forth, you traveled a far distance, say double just the one direction of motion. Here I went back and forth. But if I come back to where I started, then my change in position is 0. And if my initial position was at y equals 0, then my ending position is also at y equals 0. The definite integral symbol, once again, assuming we start at position 0 when t is a is the starting value of time, often 0, still represents the position as well. However, as an area, it doesn't represent an area under a graph. Instead, the catch or adjustment is that it represents something else. Instead, it is best described as representing what's called the signed area between the curve and the horizontal axis, which in this case is a t-axis. Emphasis on the word signed. And that's signed as in positive or negative, right? Not the sign function. Signed area between the curve and the t-axis. Here it is in a nutshell. If the graph of the velocity versus time is both above and below the axis, as t goes from a to some particular number t, then the definite integral represents this area plus this area minus this area minus this area. And since I purposely made this area bigger than that one a little bit, and this one bigger than that one, the final answer here will be negative. This plus this minus that is going to be a negative quantity. And what that means is your position is negative. Or if you prefer, your changing position is negative. Moving this way, then back this way. I'll try to model this motion. Then back again, faster, then slower, then again, back again, faster, then slower. My change in position is negative. And if I start at position 0, my new position here is negative. Here's how it plays out in an example. Constant negative acceleration example. Negative acceleration. Let's say the velocity is negative 2t plus 3. So think about this with me here. Negative 2t plus 3, that's a line with a slope of negative 2 and a vertical intercept of 3. It'll look about like that. This horizontal intercept is going to be at 1.5. 3 halves, right? Plug in t equals 3 halves into this formula. We get negative 3 plus 3 is 0. I'm letting t go as high as 4. This area minus this area is going to be negative because I made this area so much bigger than this one. The change in position will be negative. If you start at position 0, your final position will be at a negative number along the axis. And now we're going to think about what happens if we pick an arbitrary t, at least between 3 halves and 4. Once again, we'll assume we start at position 0 when t is 0. The definite integral is going to be representing now a signed area. Here's the picture. In this picture, I am assuming t is between 1.5 and 4. It would be a different picture if t was between 0 and 1.5. It would be a picture of an area of a trapezoid, actually. But I purposely wanted to put t over here to emphasize it's this area minus this area. This is the trickiest calculation, but I think also the most important one. What is this area minus that area in terms of t? This whole difference of areas, which I'm calling a signed area, and many other people call it a signed area, is the difference of the areas of two triangles. This triangle minus that one. This triangle has a fixed area. T is over there. Its area is 1/2 base times height. 1/2 times 1.5 times 3. 1/2 times 1.5, that's 3/4. Times 3 is 9/4. This area should be 2.25. What's this area? It depends on t. The base is t minus 3 halves. And the height is this distance here, which is not the second coordinate at this point, but it's opposite, because its second coordinate is negative. But I want the height to be positive. So here's the calculation. Again, this gets tricky. 1/2 base times height. Base 1 times height 1, base 2 times height 2, because you have two triangles. That's triangle 1, that's triangle 2. This distance is base 1, 1.5. This height is height 1, 3. Base 2 is this distance, t minus 3 halves. And height 2, that's the trickiest part, is the opposite of the function. The opposite of the velocity. Negative 2t plus 3 is negative when t is bigger than 1.5. So to make it a positive height, I need to put a negative sign in front of it. That's the trickiest part. This is now a positive quantity when t is bigger than 1.5. And it's this height that you see right here as a positive number. Simplify. 1/2 times 3/2 times 3, it's going to be 9/4, 2.25, like I already mentioned. Minus this, I can bring this negative sign out in front and make it a plus sign there. And then just FOIL what's left, t minus 3/2 and negative 2t plus 3. And if you do that, okay, here's the plus sign that came from combining these two minus signs. The 1/2 I'm just leaving there. T minus 3/2 times negative 2t plus 3. What? T times negative t is negative t squared. Negative 2t squared. T times negative 2t. Outside times outside is t times 3 is 3t. Inside times inside. Again, ignore this negative sign here. It's no longer there. Negative 3/2 times negative 2t. It's going to be positive 3t. 3t plus 3t is 6t. The outside and inside terms are both 3t. They add to give you 6t. And then finally, last times last is negative 3/2 times 3 is negative 9/2, which is what you see there. Bring the 1/2 through, simplify, and you get this. Negative t squared plus 3t. That is indeed an antiderivative of the original function. Differentiate this, you'll get negative 2t plus 3. Same as this. And it goes through 0 when t is 0, just like we wanted to. I didn't graph it on here, but I could have. It would look about like this. This would be the position as a function of time. Starts out going positive when the velocity is positive. Here's where the velocity becomes negative. That's t is 1.5. That's when the velocity switches sign from positive to negative. And once you get past here, whatever that happens to be, probably 3 by symmetry, then that position goes negative. I'm pretty sure this is 3 by symmetry. That is the position. We're over time. I wanted to show you some stuff on mathematics. I guess we'll save that for Wednesday.